Good morning, Andy. Today we will discuss solid state chemistry. Andy. In the morning session, we will discuss solid state chemistry. In the evening session, we will discuss quantum chemistry. Andy. Okay. So I would like to start new chapter, that is solid state. Solid state. So we know one of the classifications of matter, based on physical state. Based on physical state, we know matter is classified into three types. Based on physical state, matter is classified into three types. What are those three types? Solid state, liquid state, and gaseous state. Okay, if you see a small introduction to solids. So based on physical state, matter can be classified into three states: solid state, liquid state, and gaseous state. And we know which state is the least condensed state, and out of these three states, what is the least condensed state? That is gaseous state. And most condensed state is solid state. If you do the condensation of gases, we will get liquids. If you do the condensation of liquid, we will get solid. That means what is the most condensed state? Solid state is said to be the most condensed state. Okay, if you do the condensation of gases, we will get liquids. Condensation of liquids gives solids. Most condensed state, that means the particles, how the particles are arranged, and the particles are arranged very closely. The particles are arranged close to each other compared to liquids and gases. Compared to liquids and gases, what about the distance between the particles? And the distance between the particles is small. The particles are arranged close to each other. And compared to liquids and gases, generally solids possess high density or not? Yes, as the particles are arranged close to each other, solids possess high density compared to liquids and gases. And what about shape, mass? And solids possess definite shape or not? Yes, solids possess definite shape, mass, and volume. Whereas liquids possess what? Definite shape and volume, but no definite mass and volume, but no definite shape for liquids. The shape of liquid is the shape of the container. That depends on the container. Okay, so liquids possess what? Definite mass and volume. And whereas gases possess only definite mass, no definite shape, no definite volume. Gases do not possess definite shape and volume, only possess what? Definite mass. Whatever the mass available, the gases may occupy that entire volume, so they may not generally possess a definite volume. Okay, so solids possess definite mass, shape, volume. Liquids definite mass and volume. Gases possess only definite mass. And solids are rigid or not? Rigid, hard. They are hard compared to liquids and gases. They are not soft. Solids are rigid and incompressible. Incompressible. What is the effect of pressure on solids? And this is a solid substance. Is there any effect of pressure on this solid or no effect? And no effect. They are incompressible. Solids are rigid and incompressible. And solids show thermal properties, whether they conduct heat or not. Yes, they conduct heat. Iron rod, if you, for example, if you heat it, the transfer of heat takes place from one end to another end or not? Yes. So they have thermal properties, they conduct heat. Electrical properties, they conduct electricity. Iron rod, for example, conduct electricity. Solid shows thermal property electrical properties and magnetic properties. Solids shows thermal properties, electrical properties and magnetic properties. So these are some general characteristics of solids. Okay, out of solids, liquids, gases, this is the most condensed state. As it is the most condensed state, the particles arranged very close to each other. Particles arranged very closely means they possess high density. Next, solids have definite mass, shape and volume. They are rigid and incompressible. Effect of pressure is negligible. They show thermal properties, electrical properties and magnetic properties. In this we study electrical properties and later based on electrical properties we have conductors, insulators and semiconductors. We have conductors, insulators and semiconductors that we will see later. Okay. Next, another one of the classifications of solids I am giving. Okay, we can classify solids based on electrical properties, conductors, semiconductors, insulators. We can classify solids based on magnetic properties, paramagnetic substances, diamagnetic substances, ferro, antiferro, ferri. Like that we can classify solids based on magnetic properties. Next, based on arrangement of particles. One of the classifications of solids based on arrangement of particles. Based on arrangement of particles, solids are of two types. Those are amorphous solids and crystalline solids. Amorphous solids and crystalline solids, that classification we see. Classification of solids. Okay, on what basis we are doing this classification? Based on arrangement of particles. Based on arrangement of particles. Okay, based on arrangement of particles, solids are classified into two types. Based on arrangement of particles, solids are classified into two types. Those are crystalline solids and amorphous solids. Crystalline solids and amorphous solids. Okay, now we will see some differences between crystalline solids and amorphous solids. What about the arrangement of particles in the case of crystalline solids? Ordered arrangement of particles is observed. Ordered or regular arrangement, periodic arrangement, ordered or regular arrangement of particles is observed in the case of crystalline solids. Ordered or regular arrangement of particles is observed in the case of crystalline solids. For example, like this. Okay, here the gap is also maintained same. Regular and periodic arrangement we are saying. Regular and periodic arrangement, same gap may be maintained. This type of arrangement of particles is observed in the case of crystalline solids. Amorphous solids. What about in the case of amorphous solids? Random arrangement of particles is observed. Disordered arrangement of particles is observed. Random or disordered arrangement of particles is there. So you may take some random arrangement of particles. Okay, random or disordered arrangement of particles is observed in the case of amorphous solids. Okay, next one, this ordered arrangement is observed up to long distances. Ordered arrangement for solid state I have typed material, and that material also I will share. Okay, ordered arrangement is observed, ordered arrangement is observed up to long distances. Whether this ordered arrangement is observed up to long distances or short distances, if you see, ordered arrangement is observed up to long distances. So therefore crystalline solids possess, therefore crystalline solids possess long range order. Ordered arrangement is observed up to long distances, so therefore we say that crystalline solids possess long range order. Here, what about ordered arrangement? And ordered arrangement is observed up to short distances only. Ordered arrangement is observed, right? Same. Ordered arrangement is observed up to short distances only. So therefore amorphous solids possess short range order. Ordered arrangement is observed up to short distances only. So amorphous solids possess what? Short range order. Amorphous solids possess short range order. Okay. Examples, if you see, for crystalline solids. Okay, in this chapter, whatever the solids we are going to discuss, almost all the solids we are going to discuss in this chapter are crystalline solids only. We'll concentrate on crystalline solids only. NaCl, KCl, cesium chloride, Na2O, okay, etc. Almost all whatever we are going to discuss in this topic are crystalline solids only. Quartz, etc. If only quartz is given, crystalline solid andi. If quartz glass is given, that is amorphous solid andi. Examples for amorphous solids are plastic materials, glass materials andi. Examples for amorphous solids are plastic and glass materials andi. And high molecular weight polymers also examples. High molecular weight synthetic polymers, high molecular weight synthetic polymers andi. So polymers possess ordered arrangement or disordered arrangement andi. Polymers possess disordered arrangement andi. So plastic materials, glass materials comes under amorphous solids andi. If it is given quartz glass andi, glass comes under amorphous solid andi. Quartz contains what? Silica andi, SiO2. Next one, if you see, crystalline solids are considered as true solids and real solids andi. Crystalline solids are considered as real solids, true solids, whereas amorphous solids are considered as pseudo solids andi. Based on these differences also previously questions given, and in set exam, JLDL exam, the questions given andi. In CSIR also once a question given andi, based on this difference between amorphous and crystalline solid, only once a question given. But JLDL exams, they are giving questions andi. This question given andi, pseudo solid, DL exam, set exam, they have given andi. Okay. So amorphous solids are also considered as pseudo solids or super cooled liquids andi. They are also called as pseudo solids or super cooled liquids. Pseudo solids or super cooled liquids, since generally we know liquids possess random structure, disordered arrangement. Liquids possess disordered arrangement. Here amorphous solids also have disordered arrangement. Amorphous solids also have disordered arrangement. That is one reason that they are considered pseudo solids or super cooled liquids. And similar to liquids, they have tendency to flow. Similar to liquids, okay, similar to liquids, they have tendency to flow. They have disordered arrangement, one reason, and another one is similar to liquids, they have tendency to flow. Plastic materials and glass materials have tendency to flow or not? Yes, they have tendency to flow. If you observe glasses and window glasses in very old buildings, if you observe window glasses, if you see the thickness at the bottom, thickness of glass at the bottom is more. Thickness of the glass at the bottom part is more. That is the reason. The reason is they have tendency to flow. Okay, right? So crystalline solids are considered as true solids, and amorphous solids are considered as pseudo solids or supercooled liquids. Next difference. Crystalline solids generally possess sharp melting point, or they melt over a range అండి. Crystalline solids possess sharp melting point అండి. Crystalline solids possess sharp melting point. For example, NaCl if you take, or sugar if you take, up to certain temperature they remains in the solid state only. Whenever it reaches melting point, after reaching melting point, suddenly they changes from solid state to liquid state and solid phase to liquid phase. So they possess sharp melting point. And whereas amorphous solids do not possess sharp melting points. They do not possess sharp melting point, or they melt over a range of temperature. They melt over a range of temperature. They melt over a range of temperature. First they are softened, and while we are heating plastic material or gas material, they may not suddenly converted from solid state to liquid state. First they are softened. After that they may convert into liquid state. That means they melt over a range of temperature. Next here some ordered arrangement of particles is there. Ordered arrangement of particles is there. So therefore symmetry elements are present here. Symmetry elements are present in the case of crystalline solids. Later we will discuss symmetry elements in cubic system. And later we will discuss symmetric elements in cubic system. You write symmetric elements. So symmetric elements are present in the case of crystalline solids. For example, cubic system we will see later. Plane of symmetry present, axis of symmetry present, center of inversion also present, and that we will see later. And here disordered arrangement of particles is there. So symmetric elements are generally absent, and symmetric elements are absent. Symmetric elements are not present. And next XRD and X-ray diffraction. So X-ray diffraction is shown by these solids. That's why we can reveal the structure of crystalline solids based on X-ray diffraction. We can give the structure of crystalline solids based on X-ray diffraction. That is in our syllabus. Later we will discuss. And X-ray diffraction is shown by crystalline solids, but XRD is not shown by amorphous solids. So whatever the conditions required for X-ray diffraction, those conditions not satisfied by amorphous solids. So X-ray diffraction is not shown by amorphous solids. And this question given in CSR for 2 marks. Which of the following solids do not show XRD? In the options given amorphous solids. Amorphous solids, okay, do not show X-ray diffraction. And last one, whether crystalline solids are isotropic or anisotropic. Whether crystalline solids are isotropic or anisotropic. Anisotropic means if you measure a property in different directions, if you measure a property in different directions, if you get a different value, if you measure a property in different directions, if you get a different value, then such property is said to be anisotropic. If you measure a property in different directions, if you get same value in all the directions, if you get same value in all the directions, that is said to be isotropic. Whether crystalline solids are isotropic or anisotropic, whether we get same value or different value in different directions. I am taking a crystalline solid like this. I am taking a crystalline solid like this. Ordered arrangement of particles I am taking like this. Ordered arrangement of particles I am taking. Okay. For example, I am measuring a property in this direction. I am measuring the same property in this direction. I am measuring the same property in this direction. Okay. I am measuring the same property in this direction. Okay. Same property I am measuring in different directions. If you see, in this direction, that property is due to what? X minus ions. In this direction, that property is due to what? M plus ions. In this direction that property is due to what? In this direction that property is due to what? M plus and x minus ions. That means in all the directions are same or not same, and all the directions are not same. That means in different directions we will get a different value. That indicates that crystalline solids are anisotropic, and crystalline solids are anisotropic. Okay, whereas in the case of amorphous solids, random arrangement of the particles is observed. Random arrangement of the particles is observed. Almost we may get same value in all the directions. So amorphous solids are said to be isotropic. Amorphous solids are said to be isotropic. These are some of the differences between amorphous and crystalline solids. Okay, if you get a different value in different directions, that is said to be anisotropic. And if all the directions are almost the same, that is said to be isotropic. And anisotropic behavior of solids gives a proof for ordered arrangement. And okay, give you a proof for ordered arrangement in crystalline solids. Anisotropic behavior of crystalline solids give a proof for ordered arrangement of particles in crystalline solids. And okay, different different directions we are getting different ions. In different directions we are getting different ions. It indicates that ordered arrangement of particles is there. Okay, and one more point you may remember, that amorphous silicon and amorphous silica is used in solar cells. One of the applications of amorphous solids, if you see, amorphous silica is used in solar cells. And in solar cells, light energy converted to what? Electrical energy. And to convert light energy to electrical energy, we use amorphous silica. And one of the important applications of amorphous solids, if you see, amorphous silica is used in solar cells. And okay, so these are the differences. And ordered arrangement of particles is observed there in crystalline solids. Random arrangement, this ordered arrangement is observed up to long distances. That's why they possess long range order, they possess short range order. These are some examples. Crystalline solids are considered true solids, whereas amorphous solids are considered pseudo solids or supercooled liquids. Since their structure is similar to liquids, and similar to liquids they have tendency to flow, that's why they are considered as pseudo solids. Next one, they possess sharp melting point. They melt over a range of temperature. Symmetric elements are present due to ordered arrangement. Here absent. XRD is shown by crystalline solids, not shown by amorphous solids, and they are said to be anisotropic. These are said to be isotropic. Okay. So I'm going to next topic. Classification of crystalline solids. Classification of crystalline solids, we see briefly. Classification of crystalline solids. Almost 90% of the solid state we are going to discuss is intermediate syllabus only. And classification of crystalline solids, 90% of solid state we are going to discuss is from intermediate syllabus only. So you can refer intermediate books also, NCERT book also you can refer, or any IIT books you can follow for solid state. And only except Miller indices and XRD. And except Miller indices and XRD, all the remaining topics from intermediate syllabus only. And okay, only two topics they are not present in intermediate syllabus, and that is Miller indices and XRD. And classification of crystalline solids. And I will explain briefly. And if you want a detailed classification, you can check intermediate book. And okay, or any IIT book like OP Tandon, Singage publications, whatever you have, you may follow. Okay, right. Classification of crystalline solids. On what basis we are doing this classification? And if you see, based on interaction. And based on interaction or intermolecular forces, based on interaction or intermolecular forces, present between constant particles, based on interaction present between constant particles. So the constant particles are generally maybe atoms or ions or molecules. The constant particles may be atoms or ions or molecules. So based on interaction between constant particles, okay, or based on the nature of constant particles, crystalline solids are classified into four types. And crystalline solids are classified into four types based on intermolecular forces present between constant particles. Generally constant particles means it may be atom or ion or molecule. And crystalline solids are classified into four types. And the first one is molecular solids. And the first one is molecular solids. Molecular solids, the name itself indicates. Here what are the constituent particles? And here constituent particles, the solid is made up of what? The solid is made up of atoms or ions or molecules. And molecules, constituent particles are molecules. And as molecules are the constituent particles, they do not conduct electricity. And whether they conduct electricity or they do not conduct electricity, and they do not conduct electricity as they are molecules are the constituent particles, they do not conduct electricity. And molecular solids, in these molecular solids constituent particles are molecules. As molecules are the constituent particles, they do not conduct electricity. And again molecular solids are classified into three types. Again molecular solids are classified into three types. The first one is non-polar molecular solids, non-polar molecular solids, polar molecular solids, hydrogen bonded molecular solids. And non-polar molecular solids. And non-polar molecular solids, examples H2, N2, O2, all these if you take in the solid state. And okay, helium, neon, argon, etc. Whether all these are polar substances or non-polar substances. And all these are non-polar substances, so these are comes under what? Non-polar molecular solids. And generally the nature of intermolecular forces present between constituent particles is the nature of intermolecular forces. The nature of intermolecular forces present are London forces. And London forces are dispersion forces. London forces are dispersion forces present between constituent particles. And London or dispersion forces nothing but temporary dipoles. And temporary dipoles are called as London forces or dispersion forces. And temporary dipoles. And that means they are non-polar molecules. And they are non-polar molecules, but whenever the two molecules approach each other, temporarily the dipoles are created. And temporarily dipoles are created on the molecules. Okay, such temporary dipole forces are called as London forces or dispersion forces. And you will get in detail about London or dispersion forces in gaseous state. And once you check gaseous state, NCERT book you check, you will get in detailed discussion on London forces or dispersion forces. Various types of forces, and not only London dispersion forces, dipole forces, hydrogen bond, ion dipole forces, all these you will get in detail in gaseous state. And okay, so generally they exist in which state? And at room temperature. Generally they exist in gaseous state at room temperature. Generally they exist in gaseous state at room temperature. Since weak London forces are present, temporary dipoles are present, that's why generally they exist in gaseous state at room temperature. Their boiling points are very very low. And next one, B, polar molecular solids. And polar molecular solids, okay, the examples are polar molecules. And okay, previously considered non-polar molecules, now we have to consider polar molecules. What are polar molecules? And for example HCl, SO2, SO3, etc. HCl, SO2, SO3, CO2, etc. They are called polar molecules and hydrogen carry partial positive charge, chlorine carry partial negative charge. So dipoles are present, so therefore dipole interactions present between constant particles and dipole interactions are present between constant particles. Hydrogen carry partial positive charge, chlorine carry partial negative charge, so dipole is present. So dipole interactions present in between two HCl molecules. And third one, hydrogen bonded molecular solids. The examples are ice. Already we discussed, in ice hydrogen bonding is present. HF and HF, etc. So here, what about the nature of intermolecular forces and between constant particles and the constant particles are held together by hydrogen bonds. The constant particles are held together by hydrogen bonds. In ice, H2O molecules held together. Okay, what about the nature of interaction between two H2O molecules? Hydrogen bonds and constant particles are held together by hydrogen bonds and okay. In nonpolar molecular solids, constant particles are held together by London forces. Here constant particles are held together by dipole interactions. Here constant particles are held together by hydrogen bonds. And this is molecular solids. And okay, in molecular solids, constant particles are the molecules. The constant particles are molecules. They do not conduct electricity. These are the three types of molecular solids we have: non-polar, polar, hydrogen bonded molecular solids. Okay, this is the positive type and four types of solids we have. Four types of crystalline solids we have. The second one is ionic solids. Ionic solids. So the name itself indicates what are the constant particles. And the constant particles are ions. And what about the nature of intermolecular forces and what about the nature of interaction between ions? The interactions between ions are Coulombic attractive forces present. Or electrostatic forces present between the ions. Coulombic attractive forces or electrostatic forces present between the ions. So ions are held together in the solid by means of electrostatic forces. Electrons are held together in the solid by means of what? Electrostatic forces. Ions are held together in the solid by electrostatic forces. Generally, ionic solids whether conduct electricity or they do not conduct electricity. Ionic solids do not conduct electricity. In solid state, they do not conduct electricity. And NaCl salt whether conduct electricity or it doesn't conduct electricity. It doesn't conduct electricity. And in solid state, they cannot move. They cannot move freely. Their positions are fixed. So in solid state they do not conduct electricity. In solid state they do not conduct electricity. And in solid state they do not conduct electricity, but in molten state or aqueous state, they conduct electricity. In molten or aqueous state they conduct electricity. Molten state means direct NaCl solid we are taking and we are heating and we will get what? NaCl liquid. This is called what? Molten state. If NaCl solid, if you add to water and we will get Na plus aqueous Cl minus aqueous. That is called what? Molten state. And molten state. And if you apply electric field, under the influence of electric field, cations move towards cathode, anions move towards anode. That we will see in electrochemistry. If you put if you apply electric field, cations move towards cathode, anions move towards anode, so they conduct electricity and in molten state and aqueous state. And this is called molten state, this is called aqueous state. And in solid state they do not conduct electricity. And okay, constituent particles are ions. Ions are held together by Coulombic attractive forces or electrostatic forces. In solid state they do not conduct electricity, they are not free to conduct electricity. Strong electrostatic forces present and their positions are fixed, they cannot move freely, so they do not conduct electricity. But molten state or aqueous state, okay, they conduct electricity. And as temperature increases, what about their conductivity? And as temperature increases, conductivity increases. And since mobility of ions increases, as temperature increases, what happens to mobility of ions? Increases. Conductivity depends on what? Charge on the ions, velocity of the ions, size of the ion. And size is small, it can move fastly. And H plus ions, size is very very small, it can move fastly. Okay, conductivity depends on what? Generally ionic conductivity, later we will see again in electrochemistry, don't worry. Depends on size, charge, mobility. And so as mobility of ions increases, conductivity also increases. And so this is about ionic solids. And third one, metallic solids. Metallic solids. So here what are the constituent particles and metal atoms? Metals are the constituent particles, but generally metals have tendency to lose their electrons easily. Metals have tendency to lose their electrons easily, so metals present in the form of ions. Okay, so metallic solids are also considered as what? Metallic solids are also considered as collection of metal ions. Metallic solids are also considered as collection of metal ions in a sea of electrons. So we have sea of delocalized electrons, and those delocalized electrons can conduct electricity. Metals are good conductors of electricity or not? Yes, metals are good conductors of electricity. Their conductivity values are very very high. Why their conductivity values are very very high? And metals can lose their electrons easily. And metals are considered as what? Collection of metal ions in sea of electrons. Okay, that's why they are good conductors of electricity, or their conductivity values are high. They comes under what? And conductors. And metals comes under what? Conductors. Their conductivity values are very high. And very high. Okay, in between metal and electron, whatever the interaction present, that is called as metallic bond. And here constant particles are held together by metallic bond. Whatever the interaction present between metal ions and electrons, that interaction is called what? Metallic bond. So particles are held together by metallic bond. And particles are held together by metallic bond. As temperature increases, what about conductivity of metals? And this question given in CSIR and set exam also. And as temperature increases, what happens to conductivity? And in the case of solids, if you take in the molten state or aqueous state, what happens? And as temperature increases, conductivity also increases. In the case of metallic solids, as temperature increases electric conductivity decreases అండి. As temperature increases conductivity decreases. What happens if you see in the metals అండి? In the metals, if you increase the temperature, vibrational force, vibrations increases and oscillations increases. If you increase the temperature, oscillations increases and oscillations occurs fastly and so these oscillations may restrict the flow of electrons and so electrons flow cannot takes place freely and whenever oscillations takes place fastly, electrons cannot flow freely and so that means mobility of electrons decreases and as temperature increases, mobility of electrons decreases. Okay, what are the charge carriers in the case of ionic solids and here charge carriers are ions. Here charge carriers are what? Ions. Who carry charge and ions? Here what are the charge carriers and electrons and here charge carriers are what? Electrons. Charge carriers are electrons and electrons are the charge carriers. So whenever we are increasing the temperature, oscillations takes place fastly which may restrict the flow of electrons, so mobility of electrons decreases, so conductivity decreases and this is about metallic solids and we have four types of solids: molecular solids, ionic solids, metallic solids, and fourth one covalent solids. Covalent solids. Lakshpat. Fourth one covalent solids and covalent solids. Here constant particles, generally atoms and constant particles, atoms, constant particles are atoms. Okay, they are held together. Constant particles held together, right? Held together by what? Which forces and covalent bonds and atoms are held together by what? Covalent bonds. Okay, generally constant particles are atoms, they are held together by covalent bonds and if covalent bonds are extended up to 2 dimension only, those are called 2D covalent solids, 2-dimensional covalent solids. If covalent bonds are extended up to 2 dimension only, 2-dimensional covalent solids, and example is graphite and we know graphite sp2 hybridization planar. sp2 hybridization means planar, that means 2 dimension will get or 3 dimension and 2 dimension we will get 2-dimensional covalent solids. Next, 3-dimensional covalent solids. If the covalent bonds are extended up to 3 dimension and if covalent bonds are extended up to 3 dimension, that is called 3D covalent solid. Example diamond, we know sp3 hybridization, tetrahedral arrangement and tetrahedral arrangement means 2D or 3D and 3D, 3-dimensional covalent solid diamond. Generally they conduct electricity or they do not conduct electricity and generally covalent solids do not conduct electricity and generally covalent solids do not conduct electricity due to absence of delocalized electrons and due to absence of delocalized electrons are not present. Generally they do not conduct electricity. That's why diamond is an example for what? Insulator and diamond is an example for insulator. Generally they do not conduct electricity, but we have an exception, that is graphite. Graphite can conduct electricity and graphite can conduct electricity. sp2 hybridization, we have one free electron is there or not? Yes, one free electron is there in graphite. So graphite can conduct electricity. That's why graphite is used as inert electrode. It is used as inert electrode. It is used as inert electrode during electrolysis. Well, as it conduct electricity, it is used as inert electrode during electrolysis. It is used as inert electrode during electrolysis. Okay, in covalent solids, constituent particles are atoms. They are held together by covalent bonds. If covalent bonds are extended up to 2 dimension only, 2D covalent solids, example graphite. If they extended up to 3 dimension, 3D covalent solids, example diamond. Generally, they do not conduct electricity. Diamond also do not conduct electricity due to absence of delocalized electrons. And delocalized electrons are not present. So, a diamond is an example for insulator. But exception is there, graphite conduct electricity. That's why it is used as inert electrode during electrolysis. And if you see in graphite, it has layered type structure, and that layers can slip one over the other. And in graphite, layers can slip one over the other. That's why graphite can be used as solid lubricant. Graphite can be used as solid lubricant. So that is used to remove frictional force, and in between two surfaces, to remove frictional force, we can use graphite only. As in graphite, one layer can slip over other layer. In graphite, one layer can slip over other layers. Due to that slippery nature, graphite we can use as solid lubricant to remove frictional force between two surfaces. And right, this is about covalent solids, and these are the various types of crystalline solids we have. This is the question given and in CSIR for 2 marks. X-ray diffraction doesn't give any structural information. X-ray diffraction doesn't give any structural information for X-ray diffraction doesn't give any structural information for options given: metallic solids, ionic solids, molecular solids, amorphous solids. X-ray diffraction doesn't give any structural information for. 1 minute. Okay then. XRD doesn't give information about what? Amorphous solids. All these three comes under what? Crystalline solids. Ordered arrangement of particles is there. So therefore we can study them based on X-ray diffraction. Next one అండి. This question given and in set exam or one of the competitive exams this question is given. Class is in one of the competitive exams this question given. Glass is options given crystalline solid, set or DL exam andi ఇది ఇచ్చిన క్వశ్చన్ ఇచ్చాడు. క్రిస్టలిన్ సాలిడ్, సూపర్ కూల్డ్ లిక్విడ్, సూపర్ కూల్డ్ లిక్విడ్, సూపర్ కూల్డ్ లిక్విడ్, లిక్విడ్ క్రిస్టల్, లిక్విడ్ క్రిస్టల్, all the above. So glass is an example for what? Amorphous solid. Glass is an example for what? Amorphous solid. That is also considered as what? Pseudo solid or super cooled liquid. Glass is an example for amorphous solid, which is also considered as pseudo solid or super cooled liquid. That is option B. Next, this is also given in one of the competitive exams. Amorphous solids are, amorphous solids are, amorphous solids are options. Amorphous solids are solid substances, solid substances, solid substances in real sense, solid substances in real sense, solid substances real sense, that means real solids. Next, liquids in real sense, liquids in real sense, true liquids. Third one, super cooled liquids, super cooled liquids. And fourth one, substances, substances with definite melting point, substances with definite melting point. Amorphous solids are also called what? Super cooled liquids. Direct question given. They are not true solids, they are not true liquids, they are called pseudo solids. That question also given in one of the competitive exams, and pseudo solids, based on that also given and previously. This question given and right, the crystal comma which are good conductors of, which are good conductors of heat and electricity, which are good conductors of heat and electricity are the crystal which are good conductors of heat and electricity are options: covalent, covalent, ionic, ionic, metallic, metallic, molecular. So which are good conductors of heat and electricity? And covalent solids, they do not conduct electricity. Ionic solids do not conduct electricity. Molecular solids do not conduct electricity. Metallic solids, they conduct both heat and electricity. For example, iron rod, it conduct heat, electricity, right? Next one, Andy. Which of the following is an insulator? Which of the following is an insulator? Which of the following is an insulator? Magnesium, aluminum, diamond, diamond, silicon. Which of the following is an insulator? Direct question. So what is the insulator? And diamond is an example for insulator. Magnesium and aluminum are metals and they are good conductors of electricity. They are conductors and silicon is what? Semiconductor. Later we will see silicon is an example for semiconductor and nearly 300 practice questions are there and I will share you that those questions also from solid state. Okay, right. So I'm going to next topic and that is crystal lattice and crystal lattice or space lattice unit cell. Crystal lattice or space lattice followed by unit cell and okay, crystal lattice or space lattice, it is nothing but an array of points, group of points and space lattice is nothing but an array of points, group of points that represents so why we use that group of points? And that group of points we use to represent arrangement of particles in space, how particles are arranged in three-dimensional space. To explain that we are using group of points and that is called crystal lattice or space lattice and an array of points that represents arrangement of particles in space, that represents arrangement of particles in space, that is called crystal lattice and okay, here we are taking what? Group of points and maintain same gap and here we are taking group of points and array of points. So here these points indicates what? How particles are arranged in the space and each point corresponds to particle and that is also called as lattice point and each lattice point indicates what? Particle and each lattice point indicates what? Lattice and this is called crystal lattice and or space lattice. Okay. What is unit cell and unit cell is nothing but in this crystal lattice the smallest repeating unit and smallest repeating unit by which entire crystal forms, smallest repeating unit by which entire crystal forms is called unit cell and smallest repeating unit by which entire crystal forms, that is called unit cell. So here if you see, this is the smallest repeating unit and these units are repeated one over the other. What is the smallest repeating unit? This is the smallest repeating unit which are arranged one over the other to form entire crystal and okay, that is the smallest repeating unit which are arranged one over the other to form entire crystal and okay, this is a 2D unit cell or 3D unit cell and we are taking on plane on board and we are taking on plane on board means 2D and this is a 2D unit cell, two-dimensional unit cell and okay, this unit is repeating and okay, these units are arranged one over the other. These units are arranged one over the other to form entire crystal and such a smallest repeating unit is called unit cell. This is 2D unit cell, right? A 2D unit cell is characterized by how many parameters and A 2D unit cell is characterized by 3 parameters. A 2D unit cell is characterized by 3 parameters. What about the dimensions along x-axis and y-axis? What about the dimensions along x-axis and y-axis and angle between axis and x-axis and y-axis? So a 2D unit cell is characterized by 3 parameters. Those are what? Dimensions along x and y axis. For example, if you take xy plane dimensions along xy axis, for example a comma b, dimensions along xy axis a comma b, and angle between axis, for example alpha. Okay nandi. For example we have like this this type of units are repeating one over the other to form entire crystal. Okay, we have a crystal like this. For example, this type of unit is repeating this type of unit is repeating one over the other. So length dimension A along x-axis, dimension B, next here alpha okay, alpha may not every time 90 degrees only alpha may not every time 90 degrees only like this we will get So a 2D unit cell is characterized by 3 parameters dimensions along xy axis and angle between xy axis Now what about 3D unit cell? This is important real crystals possess 2-dimensional structures or 3-dimensional structures real crystals possess 3-dimensional structures real crystals possess 3-dimensional structures. So 3D is important Now 3D unit cell is characterized by a 3-dimensional unit cell is characterized by how many parameters? If you see, a 3D unit cell is characterized by 6 parameters okay, a 3D unit cell we can define by using how many parameters 6 parameters What are those 6 parameters? One is 6 parameters. One is dimensions dimensions along xyz axis, dimensions along xyz axis. For example, I am indicating as A, B, C dimensions along xyz axis A, B, C next angles between axis angles between axis, that is alpha, beta, gamma. Okay, a 3-dimensional unit cell is characterized by 6 parameters, dimensions along xyz axis, angles between axis, alpha, beta, gamma. For example, I am taking like this. Okay, this is origin this is A, dimension along x-axis, along y-axis, along z-axis. Next angles angles between axis this is one angle, this is another angle, and this is another angle angles between axis, alpha, beta, gamma. Okay, the smallest repeating unit is called unit cell. Okay, for example, in a building all rooms are of same type then each room is called a unit cell. Okay, in building, if all rooms are of same type, then each room is called what we can assume as unit cell. Okay, next types of unit cells and types of unit cells. Mainly unit cells are classified into two types and mainly unit cells are classified into two types. One is primitive unit cell, primitive or simple unit cell and primitive or simple unit cell. Second one is centered unit cell and unit cells are classified into two types, primitive or simple unit cell. Primitive means particles present particles present only at corners and particles present only at corners. That means face centers or body centers or edge centers. We have some other lattice points and some other lattice points are face centers, body centers, edge centers. Okay, whether these are occupied or not occupied by the particles and those are not occupied by the particles. Various lattice points present in a crystal are various lattice points present in a crystal are corners, face centers, body centers, edge centers and these are the various lattice points and at that positions the particles may present and at that positions the particles may present. But if you take primitive or simple unit cell, the particles present only at corners and for example I am taking simple cubic unit cell and simple cubic unit cell. Cube means what? Dimensions are same and a is equal to b is equal to c and okay, simple cubic unit cell. Let us consider this is simple cubic unit cell. So for a cube how many corners are possible and for a cube possesses how many corners and 8 corners. A cube has how many corners? 8 corners and simple cubic unit cell we are taking. Simple cubic unit cell we are taking. So the number of lattice points, okay, in the case of simple cubic unit cell, that is the smallest repeating unit and if you take this one and if this unit is repeating one over the other to form entire crystal and here particles are present only at what? Corners and 8 corners. At 8 corners we have 8 particles and at 8 corners we have 8 particles. This type of units are repeating one over the other to form entire crystal. Then such crystal comes under what? Simple cubic system. Then such crystal comes under what? Simple cubic system and okay, this is the smallest repeating units and this is called simple cubic unit cell. Number of lattice points are how many and 8 corners and at 8 corners we are getting and number of lattice points are 8. If you take a cube, for a cube how many corners are possible and a cube has 8 corners. How many face centers and 6 face centers and a cube has how many face centers and 6 face centers. For example, if you take this one, this is one face center and this is one phase and okay, that center is called phase center. Okay nandi, this is a phase and this is a phase. Next this is another phase, second phase and third phase. This is what? Third phase, like this and fourth phase we have. Phase center means here we will get phase center. Okay, four side and front side we have, will get one more, back side also will get one more phase and okay, this is a phase and 1 2 okay nandi, if you put like this, this is one, second one, third one, back side fourth one, top one, fifth one, bottom one, sixth one. So a phase, a cube has how many phases and 6 phases and so how many phase centers we will get and 6 phase centers and how many edges and how many edges we have and 12 edges and how many edges? 12 edges and 1 2 3 4 this edge and fifth, this one and 6th, 7th, 8th, okay, this is 9th and 10th, 11th, 12th. How many edges are there, and how many sides are there, and how many sides are there? 12 sides and 12 edges and 12 edges are 12 edge centers and edge center means this is a edge, this is a edge center, and this is edge center. Okay, this is called what? Face center, and this is called face center. This is called what? Edge center. Cube has 8 corners, 6 face centers or 6 faces, 12 edges or 12 edge centers and okay. How many body diagonals are possible and for cube? Let us consider that is a cube. Body diagonal means from one corner to opposite corner and from one corner to opposite corner and okay, this is a body diagonal which pass through body center and this is called what? Body center. How many body centers we have and one body center and one body center. How many body centers we have and one body center. This is body center and all body diagonals pass through body center and okay, this is one and okay, I am indicating like this and this is one body diagonal. Next this is corner, second corner, from this corner to this corner and from this corner to this corner and second body diagonal and from this corner to and third body diagonal. Next from this corner to fourth body diagonal. So how many body diagonals are possible? 4 body diagonals possible. Okay, 4 body diagonals. 4 body diagonals. Okay, types of unit cells we are discussing and so this is your right side and in the types of unit cells we have primitive unit cell or simple unit cell, means particles present only at corners. If you take simple cubic unit cell, the particles present only at 8 corners, so therefore we are getting number of lattice points 8 and we are getting number of lattice points 8. Second one and centered unit cell and centered unit cell. Okay, 8 corners, 12 edges, 6 face centers, and this is body center and this you may write as body center, one body center. And how many body diagonals? 4 body diagonals. This is one, and by connecting this corner and this corner and second body diagonal, by connecting this corner and this corner third body diagonal, by connecting this corner and this corner fourth body diagonal. Centered unit cell and so here particles present at corners and some other positions and so previously particles present only at corners. Now here in addition to corners some other positions also occupied by particles and that is called centered unit cell. Based on these some other positions, again these are classified into 3 types and again classified into 3 types. Centered unit cells are classified into 3 types. The first one is body centered unit cell. Body centered unit cell. Body centered unit cell, that means particles, the name itself indicates particles present at corners plus body center and particles present at corner plus body center and So particles present at corners and body centers అండి. 1 2 3 4 corners, 8 corners and 1 body center అండి. Particles present at corners and body center. Okay, this is example అండి. Example you write body centered cubic unit cell. For example, I am taking body centered cubic unit cell. For example, I am taking body centered cubic unit cell. Body centered cubic unit cell. So therefore, how many lattice points we will get andi? So number of lattice points are 8 plus 1, that is 9 andi. The number of lattice points are 9 in the case of body centered unit cell andi. Cubic in the sense A is equal to B is equal to C andi ante. Second one, face centered cubic unit cell. Face centered cubic unit cell. So the name itself indicates particles present at corners, particles present at corners plus face centers. Face centered unit cell. Face centered unit cell and cubic కాదు, sorry, face centered unit cell. Face centered unit cell, particles present at corners and face centers అండి. Cubic unit cell is one example for that. Particles present at corners and unit cell అండి, corners and face centers. Example FCC unit cell అండి, face centered cubic unit cell అండి. That is also called as CCP unit cell అండి. FCC unit cell is also called as what? CCP unit cell, face centered cubic unit cell or cubic close packed unit cell అండి. Cubic close packed unit cell. Face centered cubic unit cell or cubic close packed unit cell. Okay, same you write అండి. So 8 corners plus 6 face centers అండి. This is one face center, second face center, third face center, fourth face center, top face center, bottom face center అండి. Top face, bottom face we are indicating like this అండి. Just you assume that this corresponds to top face center, that one corresponds to bottom face center అండి. So total number of lattice points, how many will get అండి? So number of lattice points is 8 corners plus 6 face centers. So 14 lattice points we are getting అండి. In the case of face centered cubic unit cell or cubic close packed unit cell, number of lattice points are 14 అండి. C అండి. Third one, end centered unit cell అండి. End centered unit cell. End centered unit cell, the particles present at corners and only 2 opposite face centers అండి. Only 2 opposite face centers. Particles present at corners and only 2 opposite face centers అండి. The example is okay, for example we have like this and for cubic system it is not possible and some other system, just for clarity I am giving and I am not taking cubic system and so dimensions are not same. For cubic system, only simple cubic system we have, body centered cubic system and face centered cubic system and end centered cubic system is not there and for I think monoclinic system it is possible and end centered unit cell for monoclinic system. Okay, here we get 8 corners. So number of lattice points, if you observe, monoclinic system means A is not equal to B is not equal to C and you may draw like that, A is not equal to B is not equal to C and okay, 8 corners plus 2 opposite, only 2 opposite face centers and only 2 opposite face centers. So therefore we get number of lattice points are 8 plus 2, that is 10 and the number of lattice points are 10. Mainly cubic system important, and in this in this chapter we mainly concentrate on cubic system, and after that little bit on hexagonal system, and mainly we concentrate on cubic system. In cubic system we have three possibilities, and simple cubic system, body centered cubic system, face centered cubic system, and okay, right. So we discussed unit cells and their classification, and primitive unit cell means particles present only at corners. Centered unit cell means particles present at corners and some other positions. Based on some other positions we have three types: body centered, face centered, and end centered. Body centered means corner plus one center, body center, so number of lattice points 9. Face center means 8 corners plus 6 face centers, 14. End centered means 8 corners plus 2, only 2 opposite face centers, so 8 plus 2 10. And next one, and classification of crystal systems. Classification of crystal systems, Bravais lattices. So one image regarding this concept I shared in our group, and once you may check that image, and classification of crystal systems, Bravais lattices. You may take a break. And okay, after that break you will discuss. So once possible you may observe that image, and right.